Smart Buildings Academy podcast with Phil Zito, episode 471. Hey folks, Phil Zito here, and welcome to episode 471 of the Smart Buildings Academy podcast. In this episode, we are going to be talking about something that I found to be particularly interesting, which is HVAC control sequences. So you all are in for a treat. We have a 8-part series that's going to be released over the next several weeks. And this 8-part series is on HVAC control sequences. So if you do not know HVAC, if you do not know control sequences, if you do not know HVAC control sequences, this is going to be the series for you. Everything will be available at podcast.smartbuildingsacademy.com/471. Once again, that's podcast.smartbuildingsacademy.com/471. All right. Now, before we start the episode, depending on when you're listening to this, it's that time of the year. It is the one time of the year when we have the Smart Buildings Academy Black Friday extravaganza. Things are going to be a little different this year. First off, we're going to have 3 discount codes. We're going to have discount code 1, which is Black Friday 40, all caps Black Friday 40, 40% off our self-paced courses. We're going to have the code Niagara 25. We've partnered with ThinkTech to bring the self-paced TCP certification and bundle it with our training courses. So 25% off those courses using coupon code Niagara 25. And then we have our workforce development program. 30% off this with coupon code Workforce 30. You can only get these discounts through our e-commerce, which is available at courses.smartbuildingsacademy.com. Once again, that's courses.smartbuildingsacademy.com. Now here is the catch. These coupon codes are only good Friday through Monday, and there are limits. There are only 200 of the Black Friday 40 coupon codes, 100 of the Niagara 25 codes, and 50 of the Workforce 30 codes. These are the best discounts you'll ever get on our training programs. They're available for only these 4 days, first come, first serve. Once these discount codes are used up, or once Cyber Monday's over, this sale's over. So do not miss out on this opportunity. Go to courses.smartbuildingsacademy.com this Friday and use coupon code Black Friday 40 for 40% off our self-paced courses, Niagara 25 for 25% off our Niagara certification bundles, or Workforce 30 for 30% off our workforce development program. All right, folks, with that being said, let's get into the episode. So what we're going to do is I'm going to read through some control sequences, and I'm going to provide you my thoughts as we go through these sequences so that you can better understand what exactly we should be doing when we have control sequences as building automation professionals. Now, trust me, this will not be near as boring as it sounds, because when I thought to myself, I'm going to be reading control sequences, how in the world is that going to be at all entertaining? Because if anyone's ever read control sequences before, they're pretty freaking dry. But what we're going to be doing is I'm not going to just be reading these word for word. We're actually going to be talking about what's going on and the concepts that are going on, and just thoughts and things that I've picked up along the way. All right, so in this episode of this multi-part series, as I mentioned, we're going to start going through sequences. And what sequences should we start with? Well, why don't we start with the most common system we are going to interact with as a BAS professional, and that is VAV boxes, also known as variable air volume boxes, because guess what? They vary the air volume going into the space. If we think about how do we control a space, right? One of the questions we ask, and I'm giving you all a freebie here, on our skill assessment as well as on our tests that several people get wrong, surprisingly, is what is the most important variable in zone control. And we say, is it temperature, is it humidity, is it CO2, or is it airflow? And a lot of folks will ask temperature, or they'll select temperature. And I get that. I mean, after all, with a VAV box, you're controlling the temperature. But really, what are you controlling to? You're actually controlling airflow. Because at the end of the day, nothing's going to happen if you don't have the right air in that box going out the box into the space. At the end of the day, most of the VAV boxes, with the exception of reheat boxes, they really can't do anything to control zone temperature, or rather air temperature is what I mean to say. They could control zone temperature, but they are dependent on the air being conditioned by an air handling unit. So when we are talking about zone control and we're talking about VAV units, we're really talking about modulating the airflow that is going into the space so that we can modulate the air changes. And air changes are the amount of volume that is changed in a space, typically in an hour. So we'll say air changes per hour. And usually that's like 4 to 6 for average spaces. And when you move into the healthcare environment, you can go up to 10 to 20 air changes an hour. All right. So what does all of this have to do with boxes, and what do these things matter to us? Well, here's the deal. As a technician, as a programmer, as a designer, as a implementer, you are going to be spending most of your time on boxes. That is where most of the issues are going to occur, because here's the deal. If an issue occurs with an air handler or an issue occurs with a central utility plant, it's pretty easy to isolate. It's pretty easy to figure it out and fix it if you have a halfway decent HVAC knowledge and you understand how to program. The issue is that oftentimes with boxes, we're looking at a combination of physical install, we're looking at a combination of control points and programming, all of which in themselves are not very difficult. I'm not at all making it sound like programming a box or installing a box or commissioning a box is hard. It should not be hard. It should be the easiest thing you do. The problem is when there's hundreds of boxes, and that is where issues tend to abound, is when a box or whoever's installing the controls on the box or wiring it up or creating the program, they misread the sequence or they don't really think about what they're doing because they're on autopilot, and you run into mass scale issues. Now, granted, these can be fixed, but when you have to go to each box one-on-one, that can be a problem. So we're going to focus in on boxes, and we're going to focus in on a lot of concepts that come from boxes, purely because this is where you're going to spend most of your time. And if you get efficient in this area, you will realize the biggest gains. Getting more efficient on an air handler or a central utility plant is usually only going to benefit you on a handful of systems per site, whereas getting more efficient on troubleshooting, understanding, and installing VAVs and fan-powered boxes is typically going to have a much larger effect. So, VAV boxes. A individual VAV box typically controls to a zone temperature set point. So you have this thing called a process variable, which is going to be the variable you're controlling in a process being a loop of where you have a input and you have a set point, and those are compared utilizing typically a PID loop, which then drives some sort of output. Now, what's unique about VAV boxes, unlike fan control and cooling valve and reheat valve control, is that with VAV boxes, we are often utilizing a loop within a loop. So typically what will happen is we will have a minimum cooling CFM set point and a maximum cooling CFM set point. And so our zone temperature and zone set point are going to be compared, and that's going to drive a direct acting PID loop. So as zone temperature goes above zone set point, the output of the loop is going to increase. As zone temperature goes below zone set point, the output of the loop is going to decrease. That naturally is going to go into a reset block within the programming. And that reset block typically will scale between the min and max CFM. So as that 0 to 100% output of that first PID loop increases, that is going to, guess what, change a CFM set point. Okay, so as you change that CFM set point, then you have another process variable, and that process variable is the flow setting, and that could either be an external flow sensor or it could be one built into the field controller. So now you've got two PID loops, first of which is driving to zone temp, and the second of which is driving to your CFM set point. And only then can you drive to your damper actuator. So you will then drive a damper actuator, typically a round actuator that's on a little turn wheel, or rather a little turn shaft, and you're going to mount a actuator or a controller actuator to that shaft on the box and open and close that damper to control to set point. So it's a pretty straightforward sequence, but you can see where it starts to throw a lot of people for a loop if they're brand new, because it's a loop within a loop. And that's something that we really don't see too much outside of VAV boxes. Most of the rest of our control sequences are going to be a single dedicated loop per process. So when we are controlling a cooling only box, all we can do is open to minimum flow or maximum flow, and in between to control the zone temperature. As zone temperature reaches set point, the damper will go to its minimum position. I want you to understand that wording, because that's really critical, and it causes a lot of issues when people don't properly understand it. Minimum position, meaning not zero, but minimum position. Okay? Here's the deal. We are driving to a minimum CFM set point, not a zero set point. You should typically not have zero CFM as your minimum set point on a VAV box. The reason of which is that as you go and turn on your boxes, and let's say all the boxes are satisfied, and you turn on the fan, you don't want a ton of air slamming at dampers that are all at 0%, and then you're tripping your high static safety on your air handler before the boxes can even respond. By having a minimum flow position, you are then allowing one, airflow to get into the space so that you're not tripping your high statics, but you're also better able to meet the standards of ASHRAE 62.1, which require you to have a certain percentage of fresh air within spaces in order for those spaces to be occupied. Now, how do you do that? You do that by having a minimum CFM flow. That's why you will often see areas that are not consistently occupied being set to 0 CFM, and areas that are consistently occupied being set to a minimum CFM. However, my recommendation is usually to set a minimum position for all actuators. You know, it's hit or miss whether you do setting unoccupied spaces to 0 and then occupied spaces to a minimum, or if you set everything to a minimum. I prefer setting everything to a minimum, because that way I don't have to worry about it. It's one less thing I have to troubleshoot. So from there, from cooling only boxes, we make the leap to boxes with reheat. So cooling only boxes typically are within the internal parts of a building. So we're talking not the external parts of the building, but actually, I should be more clear, because external and internal parts, you may be like, what, Phil, you're saying a box is outside the building? No. What I'm saying is inside the core of the building, you have, it's kind of hard to describe on a podcast, but let's imagine a bullseye, right? A big bullseye. We've all seen bullseyes, right? We know what a bullseye looks like. So you have that little circle in the middle. That would be the internal aspect of the building, right? And inside there, we're going to have cooling only boxes. And these boxes are going to be cooling only because the theory is that properly utilized, you're naturally going to heat up inside the building with latent and sensible loads and all of that fun psychrometric stuff. And then the reheat boxes are going to line the perimeter, and their sole purpose is to keep the BTUs, keep the heat from escaping the building. And so what you'll do is you'll warm the exterior zones, often because there's thermal losses on the exterior zones. So now as we move to a VAV box with electric reheat, or with hot water reheat, or with a silicone rectifier reheat, which is also known as SCR reheat, which is basically like hot water reheat in how it's controlled, except for you are sequencing electrical stages instead of going and controlling a hot water valve. But let's talk about VAV boxes with electric reheat. So VAV boxes with electric reheat are still going to have zone temperature. You're still going to have zone set point, But now what you're introducing typically is discharge air, especially if you are wanting to make sure that your heating's working. That's the primary purpose of discharge air, by the way. A lot of folks will initially think discharge air temperatures exist in boxes for controlling purposes. Typically, they exist in boxes for high limit safeties as well as to detect that the heating is working. You will still want to drive your heating loop based off of your zone temperature. So what you'll have, right, you'll have your zone temperature and it will drive between min and max cooling CFM set points when it's in cooling mode. And when it drops below a certain threshold, it will start to go from its minimum position to its heating position. Okay? So you're going to go from minimum cooling to heating position, heating CFM position. And then, and only then, when that is achieved, will you go and start to stage on your electric heat. So how I typically like to do this is I like to use a single PID loop that is controlling to temperature. And then I will have 0 to 50% of that loop, right? So this is a reverse acting loop. 0 to 50% of that loop will go and it will drive my minimum to heating CFM, and it'll drive that loop. It'll drive a PID loop for min to heating CFM. So I'd have 0 to 50 coming out of my zone temperature loop, and that would be driving a 0 to 50, or that'd be driving a 0 to 100% output, and I would reset. And I would say, okay, that 0 to 50 is going to reset from min to heating CFM set point. Then from 50 to 100, I would take that and I would put that into a sequencer block and I would stage my electric heat. Now, if I was using hot water reheat or SCR reheat, then I would just simply take that 50 to 100% and I would stage that, or I would reset that as a 0 to 100% command, or 0 to 10 volt DC typically command out of the output. So that's how we go about controlling electric reheat. Still pretty straightforward, right? We're seeing a couple more things introduced. We're demystifying the purpose of having a discharge air temperature sensor. We're talking about why maximum CFM, or our CFM heating set point and our min and max cooling set points. And we're talking about using resets in order to turn on our airflow for our heat first, and then turn on our heating stages or our heating outputs. All right, from here, we move on to what are called fan-powered boxes. There's really two types of fan-powered boxes. We have a series fan-powered box, and we have a parallel fan-powered box. Let's go through the parallel fan-powered box first, and then we'll talk through the series fan-powered box, and we'll talk about when we use each one and why we use each one. Okay, so a parallel fan-powered box, right? With heat, typically these parallel fan-powered boxes will have a stage of heat in them. It operates pretty identically to our reheat box, right? We're going to control our min and max CFMs for cooling, and then as we fall below set point, we are going to go and drive ourselves into a new state. However, this new state is going to be that first, we turn on this fan that is parallel to the damper. Okay, so it's parallel to the damper, and what it's doing is it's drawing warm air from the plenum. The theory is that heat rises, it's going to be warmer in the plenum, and we are going to take our warm plenum air and blend it with this minimum cool air from the primary air damper. And that's going to be wonderful, right? We're going to get free heat. That's all good. And then what we're going to do after that, right, is we are going to say, hey, you know what? We're still not hitting set point. Then and only then will we go and turn on our terminal unit heat, whether that's electric or hydronic. Okay, and then we just step up the heat as normal. Now here's a couple key things to know. If you're thinking about this, the first thing you need to know is we no longer have a heating CFM. The theory now is that with the assistance of the fan and the minimum cool air from the primary air damper, we are going to satisfy the CFM requirements to get a proper heat transfer off of the coil. So we're not going to fluctuate between minimum and heating CFM in this sequence. It's going to be assumed that the fan is assisting in that. All right, so then we move up to this concept called series fan power boxes with heat. Now, generally, it is preferred to use parallel, if I could speak right, fan power boxes. And the reason why is that, as we just saw, the fan is going to be turned off when we're not in heating mode. Now, with series fan power boxes, we're going to be running the fan constantly, because here's how it's going to work, right? We are going to go and control the zone temperature set point. We are going to have our primary air damper, and it's going to modulate to allow the cool air to come in as needed. It's going to be blended with warm air circulated from the plenum by the fan, which is going to always be running. So essentially what happens is that the air that's delivered into the zone is at a constant volume and variable temperature. So this becomes a little weirder of a sequence in that we are varying temperature by controlling our damper while at the same time providing this constant volume of air. It's a little difficult to follow verbally, but if you go and draw a line, you'll start to see that, oh, this fan's in line, it's in series, it's going to draw air, and that's why it's creating this constant volume airflow scenario. And what happens now, right, is that when it starts to get cold within the space, the damper once again modulates to the minimum position, allowing less cool air to be blended with this plenum air that is still constantly going. And then the zone's going to reach set point, the zone continues not to reach set point, rather, it is going to get to the point now where the heat is going to start to engage. Now, here's the thing. I'm just going to talk real quickly about series versus parallel, why we even use fan power boxes in the first place. The first reason we use fan power boxes, by the way, is it reduces the fan having to work at the VAV unit, especially when we're using these fan power boxes on really long runs. So rather than having to have the fan work quite as hard, we offset that with running a smaller little fan and pulling from the plenum. Now, the nice thing about parallel fan power boxes over series fan power boxes is obviously we are not blending hot air with cold air that we don't need to do. We can actually just close the damper down if we are satisfied. And additionally, we don't have to run the fan constantly. So that is why you will often see folks wanting to use parallel fans. Another addition or another reason why that whole fan decision happens, and actually in favor of the series fan power boxes in lieu of the parallel fan, is noise. So oftentimes folks will choose series fan power boxes because they're always running, and it almost simulates a white noise kind of noise, rather than every time the box goes into heating mode, it slams a fan on, and that noise can be quite jarring. So that is another factor that folks consider when they're looking at utilizing series fans versus parallel fans. All right, folks, so I hope this podcast helped you better understand when you would use certain forms of terminal units, why we utilize terminal units, the thought process behind different types of terminal units, and some of the concepts around controlling them, both in programming as well as just in sequencing. All right, everybody, I hope you enjoyed that. This is the first of 8 episodes that we're going to be dropping that are going to be going in depth about HVAC sequences. So if you are struggling to figure out HVAC sequences, you are going to want to go and listen to these episodes. Once again, everything will be available at podcast.smartbuildingsacademy.com/471. Once again, this is podcast.smartbuildingsacademy.com/471. And if you're listening to this and you want to save money on courses, because I realize there's a lot of you who want to pay out of your pocket. This is the only time you can afford our courses because we do charge a premium for our courses. It's just how it is. They're really good quality. I'm not going to charge them for cheap. So once again, go to courses.smartbuildingsacademy.com starting the Friday after Thanksgiving until midnight on Cyber Monday, and use coupon codes Black Friday 40 to save 40% off of our self-paced courses, Niagara 25 to save 25% off of our Niagara training bundles, or Workforce 30 to save 30% off of our workforce development seats. These coupon codes will not last. There's only a couple hundred of them. They will go quick. Make sure you take advantage of them. Pick out your courses now so that you can be ready tomorrow when this sale goes live. Thanks a ton.